In this problem, the velocity of a locomotive depends on the distance covered. We are asked to find the total work done by all the forces during the first t seconds of its motion. So if I consider a locomotive here, okay, so I guess in this problem it is okay to consider that this locomotive travels along a straight path. So let's consider that as x-axis. So instead of s, I'm going to use x here. So the velocity will be k times square root of x. Now, as the locomotive moves, suppose if it is not moving along a straight path, suppose it is changing its direction continuously. So we know that whenever any particle changes its direction, it is because of force that is perpendicular to its direction of motion. So let's say in this case the velocity is along x-axis. I might have a force just along x-axis. Okay, so if I have such a force, then the magnitude of velocity changes. But in addition to this force, if I have a force at right angles to the velocity, so let's say Fy here. Now this force Fy will change the direction of the motion without changing the magnitude of the velocity. Okay, so such a force anyway will not do work, because whenever we calculate work done is the dot product of force and the displacement. So the force that changes the direction of motion of the locomotive will end up doing zero work, because the angle between the force and the displacement will always be 90 degrees. So I guess in this problem it is a good assumption to consider that the locomotive moves just along a straight path. So in that case, I'm just replacing s with x so that x corresponds to the position of the locomotive. Okay, so now velocity can be written as dx by dt. So dx by dt is k times square root of x. So we can separate the variables here. I have dx by square root of x is equal to k into dt. Now, if I integrate on either side, okay, at t equal to 0, the velocity is 0. So in the beginning, the position is 0. Okay, so it has not covered any distance. So the velocity is 0, the position is also 0. So at time t, let's say the position attained is x. Now here this integral can be written as integral, let's say if I take it to the numerator, I can write it as x to the power minus half into dx. So we are integrating from 0 to x, and the right hand side k is constant, so I'm pulling it out. I have integral dt. Okay, now I think I'm assuming that you are familiar with a power rule for integration. So where if you have a function x to the power n, where n is a number, okay, integral of x to the power n dx is x to the power n plus 1 by n plus 1. So we can use this here. So what do we have here? X to the power minus half plus 1 by minus half plus 1, and we are supposed to substitute the lower limit and the upper limit, and the right hand side we have k into t. Again, the lower limit is 0 and the upper limit is t. Now here, if I substitute the limits, I think in the denominator we have half, so if I flip that, I'll have a 2 in the numerator. So when I substitute x, I have x to the power half, which I can write it as square root of x And if I substitute 0, that's anyway square root of 0, so that's 0. On the right hand side, we simply have kt. So if I square on both sides, I will get the position of the locomotive as k square t square by 4. Again, I mean, if you did not change s to x, this would be the distance covered. And again, since the forces that are at right angles to its direction of motion are anyway not doing any work, I think this is a good idea to just consider that the locomotive keeps moving along a straight path. Okay, now once you have the position function, we can get the velocity. Okay, so the velocity of the locomotive, so I'll write it here. So the velocity is dx by dt. So if I keep the constants aside, I have to take a derivative of t square, which is simply 2t. So I get velocity as k square t by 2. Now, to get the acceleration, I have to take a derivative of this function, which is dv by dt. So we get here again k square by 2 is a constant. So the derivative of t is just 1. So acceleration is k square by 2. Now, in order to calculate the work done by the force, so all we have to do is take the force and then take a dot product of the force with the displacement. Because we have assumed that the locomotive is moving along a straight path, I think we don't have to worry about the dot product. So here we are going to integrate from 0th position to some position that the locomotive attains. So here the force is simply mass into acceleration and multiplied by dx. Okay, so here if I substitute the value of the acceleration and the differential in x, the dx, okay, so we get integral of mass, and the acceleration is k square by 2. So dx, we can write it as k square t by 2, and then this differential in time can be written here, dt. So instead of integrating with respect to position, now we have converted this with respect to time. So we're going to integrate from 0 to t. So if I pull the constants out of the integral, okay, so the work done will be, I have m k to the power 4 upon 4 and integral t dt. So I'm going to integrate from 0 to t. So what do we have here? So this is simply t square over 2, and then if you substitute the limits, the work done by all the forces here will be m into k to the power 4 t square upon 8.